Hello, welcome to the course is JPHY3BO3 Electrodynamics 1. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. We'll continue to discuss topics from Chapter 5, Magnetostatics. In the last couple of classes, we have discussed the motion of charged particle through a magnetic field. Today, let's try to understand the fundamental behavior of charge flow. So, measure of charge flow is known as current. So, if you consider current flow in a wire, you can define this as the charge per unit time passing through a given point. Usually, when we talk about current in a medium, we consider conducting medium, and therefore, the flow of current is nothing but flow of electron. But it need not be electrons if you take other type of materials. For example, if you consider a semiconducting material, you have electrons as well as holes, which are absence of electrons. So electron is negatively charged and hole is positively charged. So you can have a current flow because of the flow of electron. Similarly, you can have current flow because of the flow of holes as well. Similarly, if you consider a battery, the current is due to flow of ions. On the other hand, if you consider hydrogen fuel cells, the current is constituted by flow of protons. So, you can define current as the flow of charged particle, not necessarily electrons. And if you look at the direction of current flow, by convention, this is taken to be in the opposite direction of electron flow. This is because the convention was given by Benjamin Franklin, and he assumed that the current flow is due to the flow of positively charged particle. And later on, it was discovered that current flow is due to electrons which are negatively charged, but the convention remained the same. So even now, we consider the direction of current flow as opposite to the direction of electron flow. But nevertheless, you can define current in general as a product of charge density and velocity. So here there are two important components. One is the magnitude of current and one is the direction. So magnitude is given by charge density and the direction is given by velocity. So from this perspective, actually the sign of the charge is arbitrary. As long as you take care of the direction, the sign doesn't matter. So you can define current as the flow of negatively charged electron from left to right, or alternatively, you can define the same current as flow of positively charged particle from right to left. So as long as you take care of the direction, it doesn't matter whether you define current in terms of electrons or its positive counterpart. When we discussed about charge densities in electrostatics, we have seen that there are three types of charge densities: the line charge density, surface charge density, and volume charge density. Consequently, we have three types of currents. One is the line current, surface current, and the volume current. Let's first discuss about line current. So imagine that you have a wire and there is a line charge density lambda on it moving with a velocity v. So in time delta t, the charge density is going to cover a distance v delta t. Velocity is distance by time. So when you multiply velocity with time, you get the corresponding distance. Now, as we defined here, current is charge per unit time. This is the rate of change of charge. So you can define current, line current I as charge Q divided by time delta T. Now charge you can write in terms of charge density as charge density lambda multiplied by the corresponding length, which is V delta T. So the line current I is lambda V delta T divided by delta T, which is lambda V. Since current and velocity both are vectors, you can define in terms of vector parameters. So vector current I equal to lambda into vector V. So as I said earlier, whenever I bold a letter, it means that this is a vector parameter. So if you look at the fundamental definition, current I equal to charge density lambda multiplied by velocity V. And the unit of current is ampere, and from the definition of the current, this is charge by time. Charge unit is coulomb, time unit is second, so this is coulomb by second. So 1 ampere is 1 coulomb divided by second. We know that whenever a charge moves, there is a magnetic field produced around it. So the magnetic force experienced by a segment of current carrying wire. So from the Lorentz force, we know the definition of magnetic force. This is Q into V cross B. So you can take a small element of charge dq, calculate the corresponding magnetic force, and to find out the total force, you can do an integral. So this is what given in this expression here. The total magnetic force experienced by the current carrying wire is integral V cross B dq. Now charge you can write in terms of charge density as dq equal to lambda dl. Since V into lambda is nothing but current I can write it as integral I cross B dl. Now here look, the current is a vector, dl is a scalar here. But if you look at this diagram here, current flows along the wire, right? So the direction of the current as well as the direction of the wire, dl, both are same. Which means I can interchange these two and write F magnetic equal to integral scalar I into dl cross B. Okay, so basically I am interchanging this scalar and vector because both of them have the same direction. If I assume that the current through the wire is a uniform current, so this is a constant, I can take it outside the integral and write I into integral dl cross B. So that's about line current. Coming to surface current. So imagine that I have a two-dimensional surface on which there is a surface current K flowing in this particular direction. Now you can assume that there is a tiny ribbon which is running along the direction of the current flow. Let dl be the width of the ribbon. Since the width is measured perpendicular to the current flow, I can put a subscript perpendicular here. So the perpendicular width of the ribbon is dl perpendicular. Imagine that the current flowing through this small ribbon is di. Then the surface current density K is defined as di by dl perpendicular. This is nothing but current per unit width perpendicular to the flow. Or in terms of the fundamental definition, I can write surface current density K equal to the surface charge density sigma multiplied by velocity v. And what is the magnetic force? Once again, this is integral V cross B dq. Now dq I can write in terms of the charge density as sigma dA. V into sigma is nothing but current density K. So this is integral K cross B dE. Moving on to the volume current. Imagine I have a region where there is a current flowing. If I call J as the volume current, for ease of analysis, let me assume that I have a cylindrical three-dimensional region. Okay. Now I am going to imagine a small tube which is running along the direction of the current flow. Let the perpendicular cross-sectional area of this small tube be dA perpendicular and the current flowing through this small tube is di. Then the volume current density J is defined as di divided by dA perpendicular. So this is the current per unit area perpendicular to the flow. Or following the fundamental definition, I can call current density J as charge density rho multiplied by velocity V. Coming to the magnetic force, I can write dq in terms of charge density rho as rho d tau. Since velocity into rho is J, F magnetic equal to integral J cross B d tau. So if you compare charge densities and current density, you will notice that the volume charge density is nothing but charge divided by volume. On the other hand, volume current density is current divided by area. Similarly, coming to the surface definition, surface charge density is charge divided by area. On the other hand, surface current density is current divided by length. So you should remember the difference between these two densities. Let's do a quick problem. Current I is uniformly distributed over a wire of circular cross section with radius A. Find the volume current density J. So I have a cylindrical wire here. There is a uniform current I flowing through it. And what's the volume current density? Volume current density is current divided by the perpendicular area, which is nothing but the cross-sectional area. Current flowing through is the uniform current I, and the cross-sectional area for radius A is pi a square. So volume current density J equal to I divided by pi a square. Second part of the question, suppose the current density in the wire is proportional to the distance from the axis S. So J is proportional to S, or I can write for some constant K, J equal to Ks. Find the total current in the wire. Once again, going to the definition of volume current density, J equal to di divided by dA perpendicular. From this I can write di equal to J into dA perpendicular, or the total current I equal to integral J into dA perpendicular. And since this is an area element, I have to do a surface integration. And look at the symmetry here. This is a circular symmetry, right? So I can resort to the polar coordinates. So I am going to use the cylindrical polar coordinates. And look at the axis here. I have a variation along the distance, S direction. Also, I have a variation along the azimuth angle, right? So S and phi are my coordinates of interest here. So in terms of S and phi, I can write the area element dA perpendicular as area element, the line element corresponding to S, ds multiplied by line element corresponding to phi, which is S d phi. We have done this derivation in our previous classes, right? So the area element dA perpendicular is S ds d phi. Now substitute for dA perpendicular in this expression. And J I know it is Ks, so this is going to be surface integral Ks S ds d phi. So this is a double integral. I have to do integration with respect to S as well as phi. Since phi is the azimuth angle, it varies from 0 to 2 pi. So I first do the integration of d phi, apply the limit, so I get a factor of 2 pi here. K is a constant, so take these two outside the integral, and inside that I have S square ds. Limits are from 0 to a. So if you do this math, you will get 2 pi kaq divided by. So depending on the symmetry, either you can use the Cartesian coordinate system or the polar coordinate system. Now imagine that you have a three-dimensional region where there is a charge density rho residing. And some of the charges are moving out of this volume. So there is a current flow associated with it. So rho is the charge density and J is the current density originating from this rho. Okay. Now from the definition of current, you can define current I as integral J dA perpendicular. So let's invoke that definition here. And if you look at dA perpendicular, this is the perpendicular area. So instead of writing it as dA perpendicular, I can write this in terms of the area vector. Remember, area vector is always perpendicular to the area, right? So the same integral, I can write it as integral j dot dA. So the first one was a scalar definition. This is a vector definition. Since dA and j both are along the same direction, the dot product is nothing but the normal product here. So both these definitions are equivalent. And this is a surface integral, right? Surface integral j dot dA. I can convert this into volume integral using the Gauss theorem. So this is equal to volume integral divergence of j dA. Now coming back to the configuration, I had some charge density and the charges are moving out and there is a current developing here. And when the charges are moving out, what happens to the charge density inside? It's going to decrease, right? So I can define the current in terms of negative rate of change of the charge inside. So volume integral divergence of j d tau I can write as minus d by dt volume integral rho d tau. So this volume integral gives you the total charge inside, and the negative sign indicates that the charge inside is decreasing as the current is flowing out. Now using the Leibniz theorem, I can interchange this differential and integral and write it as minus volume integral dou rho by dou t d tau. Now compare these two sides. I have same volume integral on either side, which means I can equate the terms inside. So divergence of j equal to minus dou rho by dou t. This is a very important theorem in magnetostatics. This is known as the continuity equation. So what does it say? It says that current cannot appear from nowhere. Whenever there is a current, it has to be associated with a charge density. So in other words, continuity equation talks about the conservation of charges, local charges. So even though we are talking about currents in general, for now let's focus our discussion on to a special type of current known as the steady current. So steady current, as the name suggests, is a uniform current or a constant current where there is no change and also there is no charge pileup. So let's rewrite the continuity equation for the case of steady currents. As I said, since there is no change in the current, the charge density is going to be a constant. So dou rho by dou t is going to be a 0. So consequently, the divergence of j equal to 0 here. And since the current is uniform in the case of steady currents, the magnetic field associated with steady current is going to be a constant magnetic field. Before moving any further, let's try to put things into perspective here. So what did we learn so far? In electrostatics, we have seen that whenever there is a stationary charge, it has a constant electric field associated with it, and we call this as electrostatics. And now what did we learn? We learned that whenever there is a steady current, the magnetic field associated with this steady current is a constant magnetic field, and we call this as magnetostatics. So in one case you have constant electric field, in other case you have constant magnetic field. Now when you learned about electrostatics, you have seen for a given charge configuration how to calculate the field associated with the charges using the Coulomb's law. Now let's try to find out what is the magnetic field associated with a given current configuration. So this is given by the Biot-Savart law. So imagine that I have a current carrying loop. Let I be the steady current flowing through it. So now onwards, whenever I mention current, what I mean is the steady current. So I is the steady current through the loop. I'm going to choose a small segment of the wire DL prime and there is a point which is at a distance r from this dl prime. Let this r be the position vector of this point, and I want to find out what is the magnetic field at this reference point d of r. Remember, probably you had already learned this in electrostatics. In electromagnetism, we have three types of position vectors here. So imagine I have a coordinate system with respect to which I am measuring the position of different points. So the source point, its position vector I call as r prime. So everything associated with the source will have a prime notation. That's why I call this as dl prime, because this is the source of the magnetic field. Now I want to find magnetic field or electric field at a reference point. That point I call as the field point, and the position vector of that reference point is this r. And the separation between the source point and the field point is this r. So in Coulomb's law, we have written electric field E equal to 1 by 4 pi epsilon naught Q by r square. So that r square is the distance term, right? So it is this r. So these three position vectors are different. So you should understand the fundamental difference between these three. Okay. So what we do, we choose a small part of this loop, calculate the magnetic field associated with this small portion, then do an integral and calculate the total magnetic field at the reference point. Now I am not going into the details of this derivation. We will just look at the final result and infer important information from this. So according to Biot-Savart law, the magnetic field at the point r is given by mu naught over 4 pi integral I cross r cap divided by r square dl prime, where r cap is the unit vector along the displacement. Since current is flowing along the line, direction of current and the direction of the loop both are same. So I can interchange these two parameters. Since this is a steady current, its value is constant, I can take it outside the integral and write mu naught I over 4 pi integral dl prime cross r divided by r square. Here mu naught is a constant known as permeability of free space, whose value is 4 pi into 10 to the power minus 7 Newton per ampere square. The unit of magnetic field is Tesla. 1 Tesla is defined as 1 Newton divided by ampere meter. So this is for the line current. Quickly we can rewrite this expression for the case of surface current and volume current. So in the case of surface current, in place of I have surface current K, and in the place of line element I have the surface element dA prime. Similarly, in the case of volume current, instead of I have volume current J, and instead of the line element I have the volume element d tau prime. Now, what about a single moving point charge? Can I find out the magnetic field associated with a single point charge using Biot-Savart law? If you follow the definition here, I can write for a single charge B of r equal to mu naught divided by 4 pi, and current is nothing but charge density multiplied by velocity. Since I have a single charge, charge density same as charge. So I can write current as Q into V cross r cap divided by r square. Since you are dealing with single charge, there is no point in integrating, right? So you can get rid of the integral here. So this is the definition, right, according to Biot-Savart law. So mathematically this is correct, but physically this is meaningless, because Biot-Savart law can be applied only for steady current. Remember this. This can be applied only for a steady current. On the other hand, when you have a single point charge, this cannot constitute a steady current. For steady current, you need to have continuous flow of charges. So this is just a moving charge, not a current. Therefore, even though this equation is mathematically valid, this is physically invalid. So you can define Biot-Savart law only for a line current, surface current, and a volume current, not for a single charge. This law is a very important one. In fact, its scope is very wide. For any current configuration, however complex it is, you can apply this equation and find out the corresponding magnetic field. But the downside of this equation is that it's slightly tedious. So in the coming classes, you will learn that in some particular cases, if the symmetry is very favorable, you can apply another theorem known as the Ampere's law, which will yield you the result in a more quick and easy manner. Let's quickly test the applicability of Biot-Savart law. So let's take the case of a long straight wire carrying a steady current I, and we want to calculate the magnetic field at a perpendicular distance S from the wire. So this is the wire, and at a distance S, suppose a point P is the reference point here. I want to find out what is the magnetic field. As always, choose a small line element, calculate the magnetic field due to this line element, then do an integral and find out the total magnetic field. Okay. So from the definition, B of R equal to mu naught I divided by 4 pi integral dl prime cross r cap divided by r square. So let's first find out dl prime cross r cap. And what's the direction? Place your right hand along dl prime, curl it towards the r vector. So you will find that direction is out of the page. And coming to the magnitude, this is magnitude of dl prime into magnitude of r cap. R cap is the unit vector, magnitude is 1 into sine of the angle between these two. So this is sine alpha. You have another angle theta, which is the angle between s vector and r vector. So it's more practical to define everything in terms of theta here, because this is the angle between the vectors of interest here. So how do we convert alpha into theta? Look at these two angles here. Since this is alpha, this angle is 180 minus alpha, right? When you come inside this triangle, this is theta, this is 90 degrees. So I can write this angle as 180 minus 90 plus theta, which is 90 minus theta. So take sine on either side. Sine 180 minus alpha equal to sine 90 minus theta. Sine 180 minus alpha is sine alpha. Sine 90 minus theta is cos theta. So I can also define dl prime cross r cap as dl prime cos theta. Coming back to this triangle, I can write tan theta equal to L prime divided by S, or L prime equal to S tan theta. From that I can write dl prime as S is a constant, differential of tan theta is 1 by cos square theta d theta. So dl prime is S divided by cos square theta d theta. Once again, revisit the triangle. I can write cos theta equal to S divided by R, or S equal to R cos theta. From this I can write 1 by R square equal to cos square theta by S square. So I have calculated all the terms involved in this equation. Now I can substitute all of them back here and write mu naught I divided by 4 pi integral 1 over R square is cos square theta divided by S square, and dl cross R is S divided by cos square theta cos theta d theta. And what are the limits of integral? Suppose the angle at this end is theta 1 and angle at this end of the line element is theta 2. So you're integrating from theta 1 to theta 2. Cos square theta cancel. Then I have s and s square, 1s cancel. And I can take all the constants outside. So mu naught I divided by 4 pi s integral theta 1 to theta 2 cos theta d theta. When you do the integral, apply the limits, you get mu naught I by 4 pi s sin theta 2 minus sin theta 1. Let's consider a special case. Assume that the wire is infinitely long. So now what happens to the angles here? So let's look at theta 2. So theta 2 the angle from here to here. So when the wire is infinity, it's extending all the way to the infinity towards the right. So what happens? Theta 2 increases, increases, increases. Finally at infinity it reaches the value pi by 2. What about theta 1? When the wire extends all the way to infinity towards the left, so initially theta 1 decreases 0, then it increases in the negative direction and finally becomes minus pi by 2. So theta 1 is minus pi by 2, theta 2 is plus pi by 2. If you apply the values here, mu naught I divided by 4 pi s, 1 plus 1 which is 2. So you get the total magnetic field equal to mu naught I divided by 2 pi s. So this is how you apply Biot-Savart law to calculate the magnetic field associated with a given current configuration. So as I said, it is slightly tedious procedure, and in some particular cases, if you're lucky, you can apply another theorem known as the Ampere's law, which will give you this result in a much more quicker fashion. So that's for today. In the next class, we will try to understand the spatial behavior of the magnetic field. We will define what is the curl and divergence of the magnetostatic field. Thank you.